Last week, we discussed the kinematics of motion, how one describes the motion of an object by specifying its position, velocity, and acceleration as a function of time. This week, we will continue by discussing the dynamics of motion, how the application of forces on an object changes the geometry or trajectory of its motion. We will see that the applied forces and the change in trajectory are related through Newton's laws of motion. We will begin by reviewing Newton's three laws of motion. These were a landmark achievement in scientific thought. Most people who haven't studied physics tend to intuitively think in terms of the ancient mechanics of Aristotle, in which an applied force is required to maintain a body in uniform motion. Superficially, this seems to agree with our everyday experience, but only because friction plays such an important role in our everyday life. One of Newton's great insights was that applied forces cause changes in an object's motion rather than being necessary to maintain uniform motion. Newton's laws were the end result of a great deal of careful definition, observation, and reasoning by many scientists up to and including Newton. It is a fascinating and compelling chapter in the history of science, but we will not discuss that history in this course. Instead, we will simply state Newton's three laws of motion as assumed postulates or axioms and discuss their meaning and application. Finally, we will consider several specific examples of physical forces, such as gravity, contact forces exerted by a solid surface, like the so-called normal force, which acts perpendicular or normal to the surface, and friction, which acts parallel to the surface, pulling forces like tension in a rope or chain, and the force exerted by a stretched or compressed spring, described by Hooke's law. Taken as a whole, this week will show us how to connect the two sides of Newton's second law of motion, F equals ma, the dynamics or application of forces on the left-hand side, and its relation to the kinematics, the change in geometry of the object's motion or trajectory, on the right-hand side. Newton's first law tells us about the motion of isolated bodies. By an isolated body, we mean one on which the net force is zero, one that's isolated from all interactions to as great a degree as possible. Newton's first law states that an isolated body moves in a straight line at constant velocity and will continue to do so as long as it remains undisturbed. Note that that constant velocity might be zero. So for example, a body at rest, an isolated body at rest will remain at rest if left undisturbed. An isolated body moving at constant velocity will continue to move at constant velocity as long as it remains undisturbed. It turns out that it's always possible to define a coordinate system in which an isolated body moves at constant velocity, perhaps zero. Such a coordinate system is called an inertial coordinate system. So another way of stating Newton's first law is that inertial coordinate systems exist. Now it's worth pointing out that not all useful coordinate systems are inertial. The ones that aren't, we call non-inertial coordinate systems. As an example, imagine that I'm standing in an elevator that's accelerating upward. If we defined a coordinate system that moves with the elevator, that coordinate system is accelerated with respect to an observer who is at rest. In that accelerated coordinate system, an isolated body would not move at constant velocity. So there are applications where using non-inertial coordinate systems is convenient. However, in this course, we will concentrate on inertial coordinate systems in which isolated bodies move at constant velocity. What if the body is not isolated? If a force acts on a body, then it will accelerate in proportion to that force. In particular, for a point like constant mass, Newton's second law tells us that the vector force is equal to the mass times the vector acceleration. So in other words, the acceleration caused by a force is proportional to that force, and the constant of proportionality is the mass. Now there are two important points I want to make about Newton's second law. The first is that forces always involve real physical interactions. Something must be acting on the object. If nothing is acting on the object, if the object is isolated, then we know from Newton's first law that an isolated body never accelerates in an inertial frame. It moves at constant velocity. So the only way to have an object move with a velocity that's changing, that is to have an acceleration, is to have a force acting on it. And Newton's second law tells us exactly how that works. The second point I want to make is that this statement of Newton's second law, F equals ma, is actually a special case. It's for the special case of a constant point-like mass. More generally, Newton's second law is written as the force is equal to the time derivative of the momentum, p. Now, we'll talk about momentum later in this course in more detail, but I'll just tell you that the momentum for a point-like mass is defined as the mass times the velocity. Now, for a point mass that's constant, these two equations are exactly identical. If you take the derivative of m times v, where m is a constant, you just get m times the vector a, and you get the first equation back. So it's just a fancier way of writing the same thing. It doesn't convey any new information. So why do we talk about this as being the more general form? It's because this second form of Newton's second law can be generalized to a system of particles or a system where mass is flowing and the mass of something is changing. You can't describe that with F equals ma, but it's always true that for a given system, F equals dp dt. And we'll see how that works in more complicated mass flow problems later in the course. Newton's third law states that forces always come in equal and opposite pairs. One way we can write that is if you imagine two objects, object 1 and object 2, the force exerted by object 1 on object 2 is equal and opposite to the force exerted by object 2 on object 1. This makes explicit that real forces always arise from a physical interaction. For any force in a problem, you should always be able to identify the other member of the interaction pair. Newton's third law is the most subtle and sometimes the most confusing of his three laws of motion. So I'd like to do an example that will help clarify how to think about it. So I'm going to pick a very extreme example. Let's imagine the collision between a marble moving this way and a train. Moving that way. And so we'll say that the mass of the train, I'll write that as m sub train, and the mass of the marble is m sub marble. And obviously, the mass of the train is much larger. I'm going to write that as several greater than signs, much, much larger than the mass of the marble. Okay? And so the question I want to consider is, at the instant that these two objects collide, which experiences the greater force? So think about that yourself for a moment. In terms of outcomes, clearly the marble will be smashed by the train, whereas the train will not be noticeably affected by the marble. So your intuition might therefore suggest that it's the marble that feels the greater force. But that's incorrect, because Newton's third law tells us that forces come in equal and opposite pairs. And what that tells us is that each object will exert an equal but oppositely directed force on the other. Now, I chose a very extreme example to capture your attention, but that might seem like a surprising result. But Newton's third law tells us that the forces on each object are going to be equal and opposite. But just because the forces are equal doesn't mean that the motion will be equal. The accelerations of the two objects are vastly different because of their different masses. And the accelerations and the forces are related by Newton's second law, F equals ma. So if I write that in terms of the acceleration of the marble, a marble, is equal to the force divided by the mass of the marble, whereas the acceleration of the train is equal to, so since I wrote F for the force acting on the marble, I'm going to write minus F for the force acting on the train. So that's minus F divided by the mass of the train. And so if I want to look at the ratio, how big is the acceleration of the marble divided by the acceleration of the train, and let's take the absolute value so we're just talking about magnitudes here, that's going to be equal to the mass of the train divided by the mass of the marble. But the mass of the train is much, much, much larger than the mass of the marble, so the right-hand side here is a very, very big number. And that tells us that relative to the acceleration of the train, the acceleration of the marble is going to be enormous, even though the force experienced by each object is identical. Because of their different masses, their accelerations will be very different. So that gives us an example of what we mean by Newton's third law in terms of the interaction pair and equal and opposite forces acting. I want to reiterate that for any force in a problem, you should always be able to identify the other member of the interaction pair. So forces always come in pairs. It's important to keep in mind that these force pairs don't both act on the same object. They never act on the same object. The interaction pair always involves a pair of objects, two different objects. And let me just make that explicit with an example. The example I'll consider is, imagine a person standing on the ground. What are the forces acting on this person? I'll draw the force diagram here, say. There's gravity, mg, acting downwards, and there's a normal force upward exerted by the ground. And those two balance to give a net force of 0, which is why the person is standing on the ground and not sinking down into the ground, for example. Now, you might look at gravity and the normal force and wonder if those are an interaction pair, and they're not, because notice that these two forces are both acting on the same object, the person. The interaction pair always comes from realizing what is exerting the force on the object. So let's look at each of these in turn. Gravity is exerted by the Earth. So if the Earth, and this means really the entire Earth, exerts a force mg on the person, Newton's third law tells us that the person exerts a gravitational force on the entire Earth of mg upwards. Now that might seem remarkable to you if you're just standing around on the floor, that you are exerting a gravitational force on the planet, but you are. However, this is like the example we just talked about a moment ago. The masses are extremely different, even though the forces are the same. So the acceleration of the Earth due to this person's mass is negligible, because the Earth is so much more massive than the person. But Newton's third law tells us that there is a tiny acceleration on the Earth due to the person. That is the third law pair for gravity. mg downward exerted by the Earth on the person is paired with mg upward on the Earth exerted by the person. Now, for the normal force acting on the person, that force is exerted by the ground. So the ground exerts an upward force N on the person. Newton's third law tells us that that means that the person must exert a downward force N on the ground. That is the interaction law, is the interaction pair for Newton's third law for the normal force.